Hi everyone, welcome
everyone.
to this webinar, and well, glad to have you here. I see many people connected. Today we have an interesting topic that will present Chema, our CEO, and additionally, in between we are starting preparing this. We have already communicated you, additionally you will receive the email that we have a contest. We would like you to, if you want to participate about this content, we will send all the instruction by email. We have already sent the one that participate in the previous webinar. That we have a challenge, as you see. Maybe we are moving to the next slide. And the idea is that using our tool that is Frenetic AI, you can support on this to create a design that has the highest power ratio, and this has the stability. So you will take advantage of all the feature of Frenetic AI that you can select in between many topologies, and play with many inputs and get the LT Spice model, so then you can run it and get this. We have many participants at the moment. We would like to have your design to test it. We have time until this Friday at 20 GMT time. And then on next week, we are going to publish the winner, and the winner will access to our premium feature, that to our premium software that is a simulator, accessing to all the tools, all the features that you have. So it's a great opportunity to know it deeper and to add value to your day-to-day activities. So thank you a lot, and I encourage you to participate. We have one question. What is the power ratio? The efficiency?
So that's a good question. So maybe I can share the screen just to show you what do we mean. So if you arrive to our platform, Frenetic AI for designing power converters, you have three inputs here. The input voltage, output voltage, and power, and then some additional information. So if you, for example, when we are saying about radio, we are talking about this power. So let's say that I want to participate, and it's like, okay, I'm going to try to do something like, I don't know, 1,000 volts in the input, 1,000 volts in the output, and 100 kilowatts. And then I can choose a topology and see if this is working. So I'm not going to run just to allow the people to participate doing these kind of things. But this is as simple as this. Now you have to check if the results make sense and run the simulation in LTSpice. And that's all. Also, if you are, let's say, once you are playing, you will see that sometimes you will need to, I don't know, for example, limit the tune ratio, or, I don't know, or the magnetizing inductance just to make the design simpler or whatever.
Yeah, that's clear. Hope this is clear for you, Vito. We have many answers, and we would like to have more to compare. That's good.
I wanted to ask you about the Frenetic event we have yesterday in San Francisco. What about it?
Yeah, well, actually, we are the sponsors, but it's not just for Frenetic. It's the power electronic community of the Bay Area, and that we created, I think, 1 year and a half ago, more or less. This has been the fifth event, and it was amazing. Yesterday, we have a panelist that is called John DiFiore from Texas Instruments, and he was talking about power architectures. Actually, I'm going to share with you a little bit about the slide that he shared, because a lot of people will be interested in these slides. And he was explaining how to take decisions to design a power architecture, and he used as an example a robot. So so this is so let me share my screen just with the presentation. It's going to be interesting. So this was a presentation about designing the architecture of a power system, and that was the specific case for a battery power robot running from the universal input, and then having motors, a CPU, some LED indicators, and let's say, a battery, and John explained how to say take decisions for in terms of flow diagrams, but also in details for the selection of the components. So I think it was pretty interesting. And after that, we had a kind of interaction with all the audience, that people come from Meta, from Apple, from Lucid Motors, from Tesla, from Rivian, from Analog Devices, from Texas Instruments. So many companies in the Bay Area, especially in Mountain View and Sunnyvale, were coming there to test Frenetic AI, and they were giving us a lot of good feedback. And especially they were very interested in how Frenetic, let's say, this software can help them in a daily basis. So it was very interesting. We enjoyed some tacos. We end up very late, so I have slept very few hours. But yeah, it was very nice.
Wow. Also, maybe people in the chat would like to get these slides or maybe the video resume about the event. If you are interested, maybe you can respond to our email after the webinar, and we can provide you some slides or some information about it.
Just one little message before start. Remember that all the people that has already registered to this event with your work email, we have already sent the credentials so you can access to our first version of Frenetic AI. And well, with this credential, you will access to the environment that already show Chema. Be sure that it's your work email, because it only accepts the professional emails. And if not, register or join our waitlist, and we will send the credentials very soon. And now we are preparing the evolution of this, so get ready for the updates that we are going to release soon. Thank you, Chema. Now it's all yours.
Thank you, Emi. So what I'm going to do right now, so let me share my screen, is that we are going to talk. We will need a couple of webinars to go deeper. Today, just with 15 minutes, I cannot give a complete PhD class for serial voltage switching, but we can go through the topic. So before entering the topic, allows me to explain what we do. Let's say what our technology does. So we have our Frenetic Magnetic Simulator, that is the most accurate tool in the market for designing magnetics. And we have some articles and papers to demonstrate that. So we will be very open to share with you all these results from the lab, because everything we are modeling is tested in our lab. Some of the use cases that you can get from our simulator, these are cases that have been shared by our customers. So people is designing a complete complex CLLC transformers, but also they are designing low frequency magnetics, like with nanocrystalline or amorphous materials. Or in some cases, they are just testing their own design to make sure that everything is fine, or to see if they can optimize the design. So if you want to get a free demo of how the technology works and make sure that, or let's say discover if this could help you, just request a demo. But what we are going to, let's say what you have access today, and the main challenge that you have seen is about our Frenetic artificial intelligence. So the most interesting part of this technology is that we are trying to help the engineers in their process of designing power systems, just not power supplies, but power systems with all these kind of activities. And we cannot go to the lab with you, but we can try to help you to arrive to the lab in the best conditions. Some of the daily activities that our technology will support is like circuit simulation, research for new components, mechanical design, PCB layout. So there could be a lot of these tasks that we are already working in let's say, in this technology for you to be available. And actually, at the end, everything is going to be like unify the power electronic in a center point, and then connect with different tools. These tools can be our own Frenetic simulator. but also can be circuit simulators like LT-Spice, that is something is already working, or tools like Altium, or simulators like Maxwell. So this is kind of the idea and the things that are already implemented that you are already testing. But now let's move to the topic of today. So today we are going to talk about zero voltage switching. So I'm going to, if you are an expert, probably you will, let's say, know a lot of things that I'm going to explain today. So bear with me because we will end up in the more advanced stuff. But I want to start from the very, very beginning. So what is zero voltage switching? So when you design a converter, you are very worried about the efficiency. And the efficiency means reducing the losses in the converter. So what type of losses do you have in the converter? So the main losses. So you have losses. Let me pick the laser. So you have losses in the transformer. For example, this is a voltage phase shift center tap. You have losses in the transformer. You have losses in the output inductor, but also you have losses in the switches, in the semiconductors. So here in the primary side, we have this full bridge where we have 4 switches. And in the secondary, we have 2, could be switches or diodes. In this case, it's our diodes, but you also have losses here. And the losses that you have in a switch are 2 types of losses. One of the losses are due to the conduction. So when the energy, let's say the current is going from the energy source through the switch, there are losses. There are conduction losses. And these losses are coming through due to the resistor of this, let's say the equivalent resistor of this MOSFET when it's switch is working as a closed switch, like it's on. Also, you have losses when you have conduction through the reverse diode in MOSFET cases, but we are going to avoid that kind of specific losses for the moment. We are going to focus on the 2 main ones: conduction losses, that are the ones that I was saying about. You switch on this MOSFET and then the current goes through the MOSFET. So you have conduction losses, and then you have switching losses. The switching losses are the energy that you need to make this switch move, or let's say turn on or turn off. So change the status. So there are some conduction, let's say switching losses. And the switching losses are mainly due to the parasitic capacitance that you have in this switch, but also about when this is happening. So now we will go a little bit deeper about how these losses are happening. But in this slide, what I'm trying to explain is about why it's very interesting to reduce the switching losses. So the switching losses can be avoided if we achieve zero voltage switching. That will mean that we will be reducing the switching losses to almost 0. Then there would be less noise. The noise is just imagine that you have every losses you have during the switching is, imagine a door, and this door is just closing and opening just in a very hard way. So you are just making a lot of noise, bam, bam, bam. So imagine that you can do that so smoothly that nobody can know that this door is opening or closing. The second thing is that if you open the door in a very hard way, the door possibilities, the failure possibilities increase, because basically you are not, let's say, you are not taking care of the door, so you can break the door at some point. So there are a lot of interest in trying to reduce the switching losses. And in this slide, what I'm trying to explain is like, okay, what is for reducing the switching losses, achieving zero voltage switching, what can we do? So the first thing is to identify which is the main capacitance of the MOSFET that is going to be the origin of these losses, the main one. So there are a lot of parasitic capacitance in the MOSFET. There is the parasitic between the the drain and the source, but also you have between the gate and the source, and between the gate and the drain. Actually, there is a video from Sam Benjakov of this week talking about how to reduce the losses in the driving of a MOSFET. I really recommend that video. Maybe Ellie, you can put the video link in the chat so to everyone to see that video, because it's very interesting to see how he explains how the parasitic capacitance here work. He goes to a very, very detailed. I'm not going to go that deep, because for me, it's just to explain that if you go to a MOSFET data sheet, any MOSFET from, let's say, Infineon or Texas Instrument or whatever company, you will need to find the values of the parasitic capacitance. And in this case, this is the typical one that we use for this calculation, that is called COSS. But there is more parasitics that we need to consider, that are the parasitic of the transformer. There are two parasitics of the transformer, three, sorry, that are very relevant. One is the own capacitance here. So I didn't draw here, but you have a capacitance here. So let me see if I can draw. So there is, oh, sorry. So you have here a capacitor. So this capacitor is this one. So you need to consider this capacitor in the calculation. Then you have the magnetizing inductance, that is this inductance here, is going to play a role, and the leakage inductance, that is leakage or external inductor, in case that there is an additional inductor here, is playing a big role. So let's move to the next point. So what is the, let's say, the zero voltage switching conditions or scales? So the moment where this is going to happen, I mean, the big problem is happening during the switching, as I said. So what is happening is that, imagine this is the gate signal. So these are the signals that are going to switch on or switch off the MOSFETs. So in this case, this signal is, here is the MOSFET is on. So basically in this moment, when this signal is on, the current is going through this, in this way. And probably is going also through this way. I'm here. But then at some point, you're going to switch off this, and you will need to switch on this one, because always you switch on one in the leg, and then switch off, switch on the next one. So you can see here that once this is off, we need to switch on the next one. And the main goal to achieve zero voltage switching and reduce the switching losses is that once you switch off this one here in this moment, here this capacitor is charged to the input voltage, to this input voltage here. So this capacitor is charged. So you can see here this capacitor is charged to BDS2 is this one. So this capacitor is charged. So during the time that we are waiting between switching off this one and switching on this one, the goal is to discharge this capacitor from this MOSFET. So you can see that this capacitor is charged to the input voltage in this case. So what is happening during the dead time is this time is called dead time. So what is happening is that the voltage here just drop, and then when reached zero, we can switch on this one, and the energy stored here in this capacitor at the moment of the switching is zero. That means that we're going to have a very smooth switching transition without losses. The problem will be that, imagine that instead of switching on here, you switch on here, M2. If you do that, you will be switching with this energy here. So this energy here, imagine that is half of the input voltage. So what we will be saying is that the energy stored in this capacitor, so the energy is stored in a capacitor is 1 divided by 2 CV squared. So what you will be saying is that you will be doing a switching momentum where you will have to calculate the energy multiplying C by half in that momentum. So all this energy will be lost and you will generate a lot of noise. So that's the reason that is very important to make sure that when you are going to switch on your MOSFET or your device, this energy, let's say, is reached zero. And where is this energy going? This energy is going to the capacitor in the upper MOSFET that now is off. So as you can see, this is decreasing at the same time that this is increasing. So so it's basically just transferring the energy from this one to this one. This is what is happening. So if we how can I? So if we want to achieve zero voltage switching, there is a condition. There is a condition that is very important to make. That is like you need to understand that what is happening here is just to move the energy from this capacitor to this capacitor. The way to move this energy is with the current that is flowing here. So the current flowing here means that is the current that the energy that you have stored in the leakage inductance and also in the magnetizing inductance. So the energy stored here needs to be enough to move this energy from here to here. So then you can see here there is a condition for achieving zero voltage switching, that is the energy in the parasitic inductance here need to be higher than the energy stored in the different capacitors. So this actually, this is not referring just to one capacitor, it's just to the combination of these two capacitors plus the capacitor here. So this is called the equivalent capacitance. That usually is something like there are people that say that is 4, 3 C os plus. There is a paper from Sabate that is great about this input capacitor of the transformer. But this the equivalent parasitic capacitance here is the one that you can you need to use, and then what you are going to calculate is the value of your leakage inductance needed at the point that you want to reach zero voltage switching, because the zero voltage switching depends of the energy. That means that depends of the current. So at the end depends of the output power. That means that you can get zero voltage switching maybe at full load for sure. This is the load and this is the energy. So here you are always, let's say, or in this state, it's very easy to have, let's say, zero voltage switching. But when you are at very light load, this value is almost zero or very low, and then it's impossible to get, or let's say not impossible, very, very difficult to get zero voltage switching with the use of the leakage inductance. And I'm starting to go out of time and maybe too complex, but one of the key points is that sometimes, for example, this publication from Richard Redell in the 90s, is that he was saying, okay, in order to make sure that I'm going to reach zero voltage switching in where I want, but I don't want to get a very high leakage inductance in the transformer, I'm going to add an additional inductor here. And then I will increase the energy to achieve zero voltage switching naturally with this external inductor. So I don't need this critically anymore. But of course, you are increasing the complexity of the circuit because now you have an additional inductance, and usually you will need these two diodes to avoid oscillations. So since I think we are running a little bit out of time, and I don't want to make anybody arrive late to their next meetings, I'm going to do a pause here and ask you if there is any question. Well, sorry. And before moving to that, also, I wanted to explain that something that I was doing to make sure that that we can do all these designs is that I was running, I was using Frenetic AI to generate a simulation for this particular circuit. Oh, sorry. Well, actually, I ran it before. Exactly this circuit, and then I created the simulation. And now with LTSpice, you can verify, or let's say play with the zero voltage switching conditions. And I wanted to launch a challenge for the next week that is going to be a challenge about how to achieve zero voltage switching in as particular conditions. We will share next week. Without adding an external inductor and having a nice transformer. So that's going to be a challenge for the next week. So be ready for that. I see that there are questions, but please, if you can write the questions in the Q&A, it would be much easier.
Yeah. Yes, because we have two questions related to the challenge, and now I see two hands raised, but the way is to write it here. So, and now we have the question here.
Okay, I see that we have Mr. Gregory Mirsky. For you, maybe you don't know, but he's one of the best writers about articles about power electronics and magnetics. He used to write at How to Power, and he said that he has a patent for solving the problem of zero voltage switching at very low load. I think that we need to invite Gregory to give us a talk about that patent. So yeah, loving it.
Great.
Any other question? I mean, the people raising the hand, please write the questions in the chat.
Yes, yes, because don't have the micros enabled now. And in the midway, I remember that you have received the credentials to access and to simulate the scenario that Chema has already shown. And the idea is that we are going to share with you again the challenge in the email, and you can participate, you can simulate it and share your results. We have opened the contest until Friday, 20 in the afternoon, and we'll announce the winner on Monday.
Okay, we have a technical question. Okay, would you please elaborate a bit more on this C in you mentioned at the beginning? I think that you are referring to the calculation of the, seeing at the transformer. Yeah, maybe it was a kind of confusing because I call it input capacitance, but I was referring to the own capacitance of the transformer, that the capacitor that you can see, let me share my screen. So the capacitor that you see here, so basically when you are down discharging these capacitors, or let's say when you made an equivalent model, the capacitor that you will see here and you also need to consider is the capacitor of the transformer that you will find if you measure from here to here the transformer. I hope I answered the question.
Yeah, it seems to be answered, yeah. And well, I think that there are not more questions. Okay. Thanks all for the time, yeah, for being here. What almost a question here. Thanks. I know if you have any few words more, Chema. If not,
thank you very much, and please play with the challenge that Amy said. I think it's going to be very interesting. We are finding internally a lot of competition, so let's see who reached the maximum power radio with Frenetic AI topologies. I hope that we can continue the discussion about zero voltage switching. For knowing if this is interesting for you and you want us to go deeper, please let us know when we send you the links of the video and everything. Let us know, like, hey, I want to know more, and then we can go deeper to deeper details in terms of how to simulate or how to make more design or calculations. So thank you very much for coming today.
And thank you a lot for using our tool. We have been receiving many feedback about Frenetic AI, and it's the way that we are enhancing this tool. So I see many people that send the feedback connected. So thank you a lot. And well, we encourage to keep it using.
There is a last question. Yes, I think we are out of time, but let me answer this one. So it's how does that time, I guess that the question is, affect the zero voltage switching? And zero voltage switching is independent of leakage inductance in the case of secondary side modulation, in case of high frequency inverters. I'm going to answer just focusing on a full bridge phase shift. The dead time basically is affecting you in the time that you need to discharge the parasitic capacitance of the transformer. So the dead time is the time you wait while you have the switching. So let me share again, this is going to be very fast. So the dead time is the time between the switching of one MOSFET and switching on the next one. So this is the dead time. And as you can see, if this time is not enough to then load the discharge the capacitance, you will get a harsh switching. So that has a lot of impact on the zero voltage switching. For inverters, I think it's totally different, the approach in terms of how to modify that, because here depends on the current and the leakage inductance, but just answering for this specific case.
Okay, thank you, Chema. I think that we are more question.
Okay, let's take this as the last one. How to achieve zero voltage switching above 40% load? I think actually when you want to achieve zero voltage switching at higher loads, it's much easier because you have more current and more energy in the leakage inductance and the magnetizing inductance. It's going to be easier. The problem, as Gregory said, is a very low power. So, for example, the chips of the IC 28950 from Texas Instruments, they have a burst mode where at very low light loads, they try to help the system not to collapse of losses, just trying to modify the way that it works, because it's where you are going to have more problems with zero voltage switching. But above 40% of the load or 60% is relatively is easier. So can we add auxiliary inductance? Yeah, that's what we were saying about the option that Redel proposed in the 90s, and a lot of people is still using. That is like adding an external inductor. The only thing is that you need to add an external inductor plus usually 2 diodes to avoid the resonance. But yeah, that's a pretty good option.
Okay. I think that we are done. A very interesting topic, Chema.
Yeah, thank you very much for your questions. I really find very interesting the questions, and looks like I have been interesting for the people.
Okay, thank you a lot, and well, keep in touch. Thank you for being there.
Bye-bye. Thank you.
Bye-bye.